So in this example, we are going to be Eulerizing a graph, and that's how you pronounce this right up here, Eulerize. We're going to be Eulerizing. So once we make the graph, I'll show you what that means. And to Eulerize it, I'll step you through it once we go ahead and make the graph that represents this. And of course, this example is a carryover from the previous example. So we'll just go ahead and read it again. Many neighborhoods have homes equipped with electronic water meter sensors on the outside of the premises. The meter can be read remotely from a municipal worker's vehicle as they drive past the residence. Suppose the illustration shows several blocks of a neighborhood where residences are equipped with electronic meters. Determine an efficient route that a municipal worker would drive to read the meters. So here we have this neighborhood here. We're gonna overlay a graph on here, and the idea is to create an efficient route. Now, since we're going to be Eulerizing this graph, once we make the graph, we'll notice that the graph will not have an Euler path or an Euler circuit. For it to have an Euler circuit, all the vertices have to be even degree, and they're not. We could see that some of these are going to be odd. And for it to have an Euler path, exactly two have to be odd. And of course, that won't be the case here. So an efficient route is where we don't want the municipal worker driving over streets more than once or twice. So we're going to Eulerize the graph in order to keep that from occurring. So the first thing we'll do is we'll go ahead and I'm going to make the graph. And again, each intersection here will create a vertex. So I'm just going to put a vertex on each intersection here. And I'm just going around the map, which is convenient when we do it for street maps. So for each intersection. And then once we have all the vertices in, we'll connect each vertex with an edge, which essentially are the streets. So if I go from here to here, I'm going right down the street. So that's one of the benefits of when we use a street map. And we have to make sure we get every vertex going, every connection made. And we can just go diagonally here. We don't necessarily have to follow the street. Same way here. We don't necessarily have to follow the street as long as we make the proper connection. I think we got it. So that's what the graph is going to look like. Now to Eulerize it, what we want to do is we want to identify all the odd vertices. And I'm just going to circle them. So here's one here. Here's one there. This has got 3 edges. This one has 3. This one has 3. 3 edges here. Here's another odd one. 3 edges here. 3 here. 3 here, 3 here. This one has 4. And here's another odd one. And I think we got them all. And if you notice that all graphs that we make, all of them are always going to have an even number of odd vertices. So that means what we can do is we can pair up every pair of odd vertices. And when we pair them up to the one closest to them. And how do we determine what's the closest? Well, that determines the number of vertices away that they may be. Some of them are, or at least for this one, most of them are right on top of each other. So I'm going to add an edge right here. And I'm not really adding an edge. I'm just showing this. That means that if the municipal worker was to run this route, he would have to go back over this street, these intersections more than once. So here's when it's close by. Here's when it's close by. Now this one doesn't seem to have one to close by. It looks like it's this one here, but this one is already paired up. So I wouldn't double pair them, as I call it. So I would have to pair this one up with here. And the only way to be able to get here is I have to go past this vertex here. So I would have to put an edge here and add another edge right here. I could then pair up these two and then finally pair up these. So an efficient route would mean that there would be an extra 1, 2, 3, 4, 5, 6, 7 edges. We'd have to have 7 more edges, or in other words, the municipal worker would be driving over 7 streets or between these vertices 7 more times.